Good morning. I hope I'm audible.
Yes, sir.
Okay,
Yes, sir.
so let us get started. Uh, I hope this is visible now. Okay, so we are on module 31. So we have just for a quick recap, uh, we have tried to do a solution for the staff salary processing using function pointers in C. And then we have looked at solutions in C++ using non-polymorphic as well as polymorphic hierarchy. We saw improvements in that, and I had also requested you to look at further improvements, and some of you have very encouragingly provided nice ideas for solutions, and they're working on it. If you have not had a time to look at, please look at that, and I would be happy to get your mail and suggest you on further improvements. Now, I'll quickly recap on what you have done, and then we'll go on to something which is a little bit inside of the system as to when we do this polymorphic functions, virtual functions, then how does this polymorphic dispatch actually really work? How do you subsume the function pointers of C inside the language construct of virtual functions to make it work? So that is what will be the starting point. Then we'll move on to other topics. So you all remember the statement of the staff salary processing. This is what we did with three kinds of staff. In C, these are the questions and answers that we made. And based on that, we made a solution in C, which was kind of had a lot of problems in terms of not having encapsulation and having to add the enumerated type, do things based on the enumerated type, which was certainly not a very easy, nice way to do this. But we could somewhat make this look better if instead of every time checking on the employee type, if we kind of make a correspondence between the enumerated value of the type, which is if I go back one slide on slide 6, you can see there are three enumerated values: engineer, manager, and director. So this will be 0, 1, and 2. So if we keep that low level stuff in mind, what we can do, we can create an array of function pointers, where at the 0th location we place the process salary for engineer, then the process salary for manager, then process salary for director, like this. And this is the staff collection, which I have created as an explicit array of constructed objects with their type. That is, the unions are put in. And then I write a code which in C is pretty uniform. Like if I add more types, I will certainly need to add that corresponding salary processing function to this array, in this array, and certainly have to add those in the classes, in the structures above. But this actual processing code, which is iterating over this array of stuff and applying the function, does not need to change. But we have to be very careful to keep the correspondence between the enumerated type position and the position of the function pointer here. So this is a basic function pointer solution. And in C++, we are trying to subsume this in terms of the language construct of virtual functions. So again, in C++, we do this by a polymorphic hierarchy. We have seen all this. We have seen this code before. And here are the different engineers created. And those are put in terms of the staff array, and we have a very uniform salary processing code. The advantage here is now we do not need to remember the specific type information, neither we need to pass that, nor we need to have the care to remember that the function pointer of a specific type of employee needs to occur at a specific position in the function pointer array. And we have a set of polymorphic functions, all of them called process salary. Depending on the dynamic type of the object, it will call that. So if we extend any number of classes on this, as long as we are on this hierarchy and we are rooted at the basic root class engineer, which is a concrete class in this case, the whole application code will not need any change. So this uniformity and type safety is very important. So for a final comparison, this is what between C and C++. Of course, the C++ solution can be further improved. Like in terms of creating these objects and putting them in a collection naturally, the question is, should we have an array and do this, which is, you think of if you have 2000 engineers, and if you have to do this, this will become enormously, humongously complicated, right? You cannot do this. So possibly you are taking the employee information from the input. So one obvious way to improve this, which some of your friends have already suggested, is that instead of having an array, we use a vector, so that from the constructor of the respective object itself, when the object is constructed, we can push back the corresponding this pointer, that object pointer, onto that vector. So that vector will always have the collection of all employees. And then instead of traversing it in this cumbersome manner, we can do an iteration on that vector. We can have an iterator and just invoke on that iterator. So that will make it even more compact and easy to use system. Of course, those things are finer improvements. Now, so in terms of representation, C had struct. This is replaced by polymorphic hierarchy. Initialization functions have been taken over by constructor, destructor. Array of union wrappers is now array of base class pointers, which could also be vector of base class pointers, which would be even better. We had functions of structure. Now we have put them inside the class member function, which are virtual functions. And this function switch and function pointers is now achieved by the virtual function. So we do not get to see any function pointer anymore. Depending on the dynamic type, it gets invoked. Right. So this is a side-by-side comparison of the code. You can see the similarity between, I mean, kind of in C, we are kind of trying to simulate the function pointer based C++ kind of thing, but this PS func array is a pain point. This E type is a pain point, and so on. Extensions is obviously a pain point, and so on. Right. So this is what we have got so far. Now, what we want to move on to is to give you some insight into actually how virtual function pointers are, or virtual functions are implemented. So let us think about this simple base class. Right, they have a base class B with some data member I. It's inconsequential in that way. I have a constructor, and then I have a non-polymorphic function f, right? So it's not a virtual function. So its actual signature is b : f. It has a invisible this pointer, which is b star const. It's a const pointer, and then the parameter. So this is what the compiler actually gets to implement, gets to see. And then I have a virtual function whose pointer is also, whose signature is also similar. So I construct an object B of this class, and I take a pointer to the B type and put its address. Now, this is just for illustration. I show what is the actual source information expression, that is what we write, and on right what we show what is the actual expression that the compiler compiles, compiler creates from this. The first is invocation of the function f by b, directly on the object, right? Non-polymorphic function directly being invoked on the object. So the object's address has to be passed as a invisible parameter. So the function actually called is b::f, obviously, and you pass the address %b, the other parameters remain same. So this is what the compiled version is. In the second, if you do p pointer f, the the non-polymorphic function again, then you have p is a pointer to this object of b type. So it calls b::f, passes p, that is in place of this pointer, and the parameter 25. This is straightforward. So this is what is known as static binding, because from the object or from the pointer, you statically can create what function you are going to call. Right? Think about now the polymorphic function, right? G, the virtual function. Again, call it on the object, b.g35. Now, if you call b.g35, then you have the static binding again. On the object, it always gives you static binding. So what you call is b::g ampersand b, which is this pointer, and 5. So b.f and b.g have no difference in the treatment, so as long as you are calling it on the object. Now, when you call it as p pointer g, you do something very different because it is polymorphic. So let us understand how the compiler implements it. Here is the object. On left, you can see the object. Object has one data member, I, which is b::i, which by construction will get this value 100. For the I'm showing for the instance small b here. Now, the moment a class has a polymorphic function, what it gets is an additional invisible pointer. This is called a virtual function pointer table address. Right? So what you have is, for this class, this is static for the class. This is not object specific. For this class, you make a list of function pointers, kind of an array of function pointers, as we were doing in C, in which you put the polymorphic functions, pointers to these polymorphic functions, one after the other. So we have only one polymorphic function here, which is G. So this is the function signature. So it creates a VFT, virtual function table. Some call it virtual function pointer table. Some call it virtual function table, whatever way you call it. It's a virtual function table where at the 0th location, you put this particular function signature or the particular function pointer. Okay. And in your object, this VFT will point to this table. Now, mind you, it is not only for this object B. Any object that I construct of this class will have this VFT pointer, and it will point to the same virtual function table. Right. So what I say, when I know that this is a virtual function, and when I know that I'm invoking it with a pointer, unlike this non-virtual case, I do not pass the pointer. I take the pointer, which is pointed to this object, dereference to get the virtual function table pointer, which is this array, VFT, and I know that this function is the first in the list of virtual functions in this class. It happens to have only one. So it is indexed by 0, the first one. So I take p pointer VFT0, which is this function pointer, and I call that function by p45. This call remains same, but in place of b::f, which was statically put here, or B colon colon G, which was statically put here, I put this in direction. This eventually calls G. In this case, since I have no specialization, no variations, it eventually calls the same function. But you can see that if I change this function somehow here at the runtime, somehow, then it will call a different function. Right? So this is the main mechanism of the indirection and virtual table. Let us now look at the right side of the derived class. Of this base class B, I have a derived class D, which has another data member. Just for illustration, it has a constructor. Again, it overrides the non-virtual function, non-polymorphic function f. So it becomes D colon colon f, etc. It also overrides the polymorphic function G from the base class B and puts its own definition for G. So it becomes D colon colon G if constant. Now it constructs an object of class D. It takes a base class pointer and puts that address. Upcast, permissible, right? Now you look at what happens to the calls when you call it with respect to this D. If you call D.f by the object, f has been overwritten in class D, so it calls D colon colon f ampersand D. Does not call B colon colon f anymore because you have overridden. If you had not overridden, it would have called the function in B. If you do P pointer f is non-polymorphic, so it calls D colon colon f because it is overridden. Now we'll take a look at the polymorphic case. If it calls D.G directly by the object, it still statically binds and calls D colon colon G because it is overridden. If you now make a call to P pointer G, what does it call? It calls P pointer VFT0 P45, right? Because G is polymorphic, as we saw in the last case. Now, what it does at the time of object construction, it now knows that this polymorphic function G in B has been overridden by D. So in the virtual function table, it replaces, for class D, it replaces B colon colon G by D colon colon G, this function. But if you look between these two calls, P pointer VFT0, P pointer VFT0, there is no difference. So what it's getting compiled at the static time is not different. But what it gets executed, in this case, it will, in case P is pointing to a B class object, it uses this virtual function table calls B colon colon G. If it is a D object, it calls D colon colon G through this mechanism. So this virtual function table is the basic instrument through which the virtual functions or polymorphic functions get implemented. As you override a polymorphic function, in the same position in the virtual function table, the overridden function's signature gets replaced. Now, this positioning is very important because here you have no idea about the name of the function. So what you are saying is, let us call the 0th function. So whatever is 0th in B has to be 0th in D as well. So if you do not override, it will simply copy the signature of the B function here. But the position of the functions in the virtual function table are always in the order in which they are defined in the class. Now, if some of them are overridden by the derived class, then in those corresponding function pointer slots, the signature or the pointer to the derived class overridden function is replaced in place of the base class polymorphic function. So that's the basic mechanism of virtual function pointer table. So Whenever a class defines a virtual function, a hidden member variable is added to the class, which points to an array of pointers, virtual functions called the virtual function table. VFT pointers are used at runtime to invoke the appropriate function implementation, because at compile time, it may not yet be known if the base function is to be called or the derived one implemented by the class that inherits has to be called. I've mentioned VFT is class specific. All instances of the class has the same VFT. VFT carries runtime type information. We will talk about this little later. Right? So let us see a little bit more detailed example. So I have, yes?
So one thing, the VFT is created only for the base class, or every time we
every class has a corresponding VFT, right? I mean, look at slide 13. Base class has its own VFT with its own polymorphic function filled in. Derived class will have its own VFT with its polymorphic function filled in. So if it is not overriding, if it's simply inheriting, it will have the base class function pointer. If it is overriding, it will have its own function pointer. So that when the compiler compiles, it is just compiling based on the position of the function in the virtual function table. It does not need to know whether it is B::G or it is D::G. Making sense?
Yes, sir.
Okay. Let's go through the next example, which is a little bit more detailed. I think that the replacement is not shown. The replacement, non-replacement is not shown in the earlier example. Let's go through this, then you ask again if you have doubts. Okay. So I have a base class A, which has two polymorphic function f and g and a non-polymorphic function h. I've derived class B from A, where I have overridden f, which is a polymorphic function in A. I have not overridden G. So I will just inherit the G of class A. And then I have overridden function H in class B, but I have made it polymorphic. Then in class C, I have further derived, specialized from class B, where I have overridden the polymorphic function G. B did not have its own version of G. So it is actually the version in A that was inherited by B and is now overridden by C. And it has also overridden the polymorphic function H that class B had. This is the situation. Right? I have two objects of A and B. I'm sorry, A and B, and I do this invocation. Okay. To see what the compiled version would look like. Okay. Now let us first look at the layout of the virtual function tables. Class A has two virtual functions, f and g, two polymorphic functions. So its virtual function table has two entries, A::f, A::g. The 0th slot goes to the first function f, first slot goes to g. This is a virtual function table for class A to be shared by all objects of this class. For class B, I have a virtual function table which has naturally two as I inherit from A, and I have made another function polymorphic H, so it has now 3 slots. Now 2 are already filled up, 0 and 1, so this goes as position 2. Now what happens? It is inheriting from A, function f, it is inheriting from A and overriding here. So in the 0th position, A::f is replaced in this virtual function table by B::f. Then G, it is inheriting but not overriding. So in the position 1, A::G is just copied because it has no separate overridden function for itself. And H is added, so it comes as a position 2. Now come to C, it gets the virtual function table of B, it's inheriting from that. It has not overridden F. So at the 0th position, the function remains B colon colon F. In position 1, it got the inherited function from A, inherited function G from A colon colon G, but it has overridden. So it gets overridden here, C colon colon G. In position 2, it got the virtual function defined in class B. So that gets replaced by the overridden form C colon colon H. So it will keep on going like this. So you always inherit the entire virtual function table from your parent, and then you replace those function pointers, those polymorphic function pointers, which you have overridden in that class. Right? And you can now see that how this whole thing will start behaving polymorphically. So so I'm not showing the invocations by object, because that will always be static. That will always take the type of the object and call the corresponding function as inherited or overridden, whatever. Now, if I do it by pointer, suppose I'm doing it by a pointer to class A, PA. Okay. Now, if I call PA pointer F2, so what will it do? It knows that the pointer type is A, so it knows that it has to refer to the virtual function table of A. It has VFT0. F is at VFT0. So it replaces this PA pointer F by VFT0 and then passes whatever the parameters are. If it invokes G, it has to replace by VFT1. That is the position it has. If you do PA pointer H, it is a non-virtual function. So it directly calls the H function in A. So it is A colon colon H. Similarly, it does not matter as to what you are passing on this. Whatever you pass, it will always call the A colon colon H. You can pass a B class pointer also, because it is A star. It will mean an upcast and going. Now, let us think in terms of pointer B, PB. If you do PB pointer F, then you know that you are pointing to some object which is class B or specialization. It cannot be class A. Right? So PB pointer F is PB pointer VFT0 here, which is B colon colon F, because it is overridden. If you do PB pointer G, it is PB pointer VFT1, which is A colon colon G, because you have not overridden here. If you do PB pointer H, it is VFT, PB pointer VFT2, because it is B colon colon H. Similarly for the other. And since here we have changed the signature little bit, this is allowed in overriding, that I can use a derived class pointer in place of a base class pointer while I'm overriding. So it can now pass either ampersand A or it can pass ampersand B here. And that is what goes in place of this VFT. You can extend this for class C again. So this is what exactly happens in case of virtual functions as you keep on adding them. And that is the reason that you inherit the virtual functions, or rather the polymorphicity of the function through the virtual function table from base to derived, is the reason behind saying that once a function becomes virtual in a class, it will remain virtual all through the subsequent hierarchy from that class. Because the moment the compiler gets a virtual function, it gets inserted in the virtual function table and gets inherited by the subsequent classes that are derived from it. And therefore, the compiler changes the style from static binding like A colon colon H to dynamic binding like PB pointer VFT2. Right? So now, whatever object you are, if PA, whatever object PA is actually pointing to, you will go to that corresponding VFT. If PA is pointing to a B class object, you will go to this corresponding VFT and invoke that object. Obviously, if a function is not defined in a particular base class, then naturally through that pointer you will not be able to access it. Okay, so this is about the virtual function pointer table. Let me go back and see if there are questions.
Sir, can you go to slide number 13?
Slide number 13. Let me go to slide number 13. I'm on slide number 13.
Yes, on the right, when
Yes.
we are calling f from the pointer p, sir, shouldn't it be b::f?
No, it has been overridden.
Sir, but it has not been declared virtual in the base class.
No. This is now, what is P? Oh, you're right. You are right. This is a typo. This is a typo. Absolutely right. This will not call this function. D.f will call. Thank you very much. This is a typo because f is of type B, and this is statically bound. So P pointer f is using the type of B, and in B this is a non-virtual function, polymorphic function. So this will be B::f. I should change this. I'll correct this. Thank you very much. Any other question? Thanks for pointing out. Small things get missed in the example. Thanks a lot. Any other question, friends? No. Okay. Casting is a very, very important factor in C++. So you know about casting from C. PDF course, you obviously knows that one type being used for another type is casting. That could be implicit, that could be explicit. And so we'll see what happens in C and what happens in C++. And so you need to cast to convert a type of an object, expression, or function to another type. That is why you need that. There could be silent implicit conversions, like standard C++ conversions, user-defined conversions. We'll talk about that. Or it could be explicit, where you're saying that I want this casting to be done. There are conversions that are not possible through implicit mechanisms, so you need to write explicit casting. Also, writing casting everywhere explicitly is very useful and is recommended as a like a kind of standard quality coding guideline, because if you have done an implicit casting, then anybody reading through the code will not be conscious about the fact that the casting has happened. But if you do an explicit casting, then it will be possible to see that written in the code. So that's, we'll come to that more. So to perform a typecast, the compiler allocates temporary storage, initialized temporarily with the value being cast. This is something which we usually miss in the concept. We say that, well, I'm casting an integer to a double, or casting a double to an integer. What will happen? I'll just cast, change the value. No, there's no magic to change a value. If you want to change a value from a double representation to an int representation, you need to run an algorithm, right? Because that's a conversion. Like you change from a decimal representation to a binary representation. You need to run a code. You need to run a function. You need to run an algorithm. So similarly, if you have a double value and you want to use it as an int value, you cannot just use it. You have to run an algorithm, right? So behind every cast, at least behind most of the cast operator, there is an inherent operator function invocation that is involved. In some cases, this invocation is inserted by the compiler itself. We call it the implicit casting. In some cases, we tell the compiler that I want this casting operator to be invoked. That is explicit casting, right? So always remember that casting is not a kind of a passive phenomenon. It is not a data re-representation. It is actually a computation. So it can always be thought of in terms of a function. It helps to think it in terms of a function. Now that function could be inline, that function could be implicitly invoked, that function could be explicitly invoked, but it is
Sir, you are not audible.
Sir, you are muted.
Am I audible again?
Yes,
sir.
sir.
I'd lost connection unzitterily. So I'm back to slide 4, module 32. So we have this double function. We all understand what it means. It says that it takes two integers. It casts I to double explicitly. This is explicit casting. And then it is dividing by j, which is a mixed mode operation. I'm talking purely C PDF. So this is a mixed mode operation. One is double, another is int. So it has to do an implicit casting and then do the operation in double, right? So that is what it means. So what it has to do, so there is two casting involved. One is I is explicitly to be cast to double.
Excuse me, sir. Sir,
Yes.
the slides are not visible.
Slides
You
are
can
not
just lower your
visible.
voice. Yes.
That is, the system does not want to work consistently. Let me go out and come back again. Am I audible?
Yes, sir.
Yes, sir.
Is it visible now? Hello?
Not yet, sir.
It's visible now, sir.
Okay, okay. So we'll continue. So we know that in this example, there are two castings that are happening, one explicitly and one implicitly. Now, look at what the compiler actually has to do. Compiler is actually constructing a double object temp I from I. So this involves the construction of double, which may not be, available to us because there's a built-in constructor. Similarly, it constructs a temp j which is of double type with j. So there are two constructions happening here, which is actually the conversion. And then it does a return of this temp values, which are the cast values. Right. So this is actually what is going on, right, behind. So there are function calls. There are function calls involves in this here. Okay, so this is some of the things that we have discussed earlier. So this is casting is performed when a value is used in place of other. I3 double 2.5 double. This is obviously a casting done. Casting can be implicit, explicit. These things we have seen. Implicit casting between unrelated classes is not permitted. We have seen that as well. And we have seen these examples. These are all examples that we had seen in the C style casting earlier. Right. And we have seen that the upcasting is safe and in the C style, and the downcasting is not. Now let us look at the casting in C and C++. Right. So in C, what you have implicit cast and you have explicit C style casting. That is, you can put the bracket and put it. It loses the type information in several contexts, and it also lacks the clarity of semantics. In C++, it performs fresh inference of type without change of value. Or it can perform fresh inference of type with change of value. Both are possible, depends on the context. When it has to change the value, it has to use implicit, it can use implicit computation, or it can use explicit or user-defined computation. For example, a fresh inference of type without change of value is, say, a pointer. You have a pointer to certain type, and you are casting it to a void type pointer. So that value will not change, but it's the type information that's changing. But when you are casting from integer to double, it is not only the type is changing, actually the value is changing. And if you have defined that conversion, then it is explicit user-defined conversion. And it tries to preserve type information in all contexts, provides clear semantics through cast operators. There are 4 cast operators. And the advantage of having cast operators is that these are explicit texts in your code. So you can actually grep, you can actually search and find these operators occurring in the code. So you know these are the points where the casting has actually happened. If you do a C style cast, say double to int, and within bracket you have written int, you cannot grep by int, because int will occur at so many places in variable declarations, in declarations of function return types, and so on. Whereas these are specific keywords, very unique keywords, which can be easily found out. So it improves the readability of the program to a great extent. So C style cast must always be avoided in C++. A cast operator takes an expression of source type that is implicit from the expression, because the source expression type is known from the expression itself, and convert it to an expression of the target type. Now the target type you may not always know. So it need to provide it explicitly in different contexts. And you follow the semantics of that operator. Use of cast operator increases robustness by generating errors in static and dynamic time. We'll see how that happens. Now, these 4 casts, so this is how they are written. So you have a keyword which defines that cast, const cast, say. Then within angle bracket, you provide the target type. And within parenthesis, you provide the expression that you want to cast. So it explicitly overrides const and or volatile in a cast because you are doing a const cast. It usually does not perform computation or change of value because constness is a sense of how you want to use it, right? So it is not changing the value of the expression, but it only says that whether you want it const or you do not want it const and so on, right? Non-const and so on. Static cast, on the other hand, is the most widely used static cast type expression. It performs a non-polymorphic cast. So it can be used in certain contexts only, performs computation to change value. It will change the value by, yes? Any questions? So it performs computation to change value either implicitly or through user defined. Right. So this is a second type of casting that you can do. Please mute yourself. Please mute yourself. Please mute. Kindly mute. Kindly mute. Then we have reinterpret cast, which can cast between absolutely unrelated object types. It does not perform any computation. It just reinterprets the value. We'll see. And it has very limited use. Typically, it is used to cast between pointer and integer. And finally, you have dynamic cast, which performs a runtime casting, particularly when we want to do downcast. So it performs predefined computation. It can set a null value for a pointer or can throw an exception for a reference. So these are the different cast operators. We'll now see examples to understand more. So first, the const cast. It converts between types with different const volatile qualification. Only const cast may be used to cast away constness or volatility. You cannot do anything else. It usually does not perform computation or change value. So let us look at here. So I have a class A with a constructor. I have a get function, which is const function, and a set function, which is not const. We have seen all this. Then I have a print function. In the main, I have defined a pointer to const character because I'm keeping a constant string here. I cannot call print on this variable C because print takes a pointer to non-constant character. So it can potentially change it. And I know C is a pointer to constant character, so it cannot be changed. So there's a violation. So I cannot pass C as a pointer to print. It will say that I cannot convert from const cat star to cat star. But I can remove the constness away by saying take C, which is const cat star, and put the target type as cat star. So I'm forcibly saying that I'm removing the constness away. I know, I don't care. I'm removing the constness away. Then the resultant type of C now after this conversion is cat star, and I can call this function. Right? So now this is risky to do, but the advantage is since you are writing const cast at any point of time, you could search for it and find out where you have done it. Let's take more example. Say const A ampersand, const A1. Right? So you have constructed an object of class A as a constant object. So you can call a.get because it's a constant member function. You cannot naturally call a.set because set is not a constant member function. It can be called only on non-constant objects. So now I cast A to remove the constness of this object, small a. So what I say, I cast A to a reference. I create a reference A ampersand. So you can see that through this constness, temporarily I'm creating a reference, and that reference is a non-constant reference to the object. So that reference now allows me to call set A, set function. But it cannot, it can do this, but it cannot remove the constness of the object altogether. So if I try to make object A as non-constant, that is not allowed. It will not be able to convert from const A to A. It can make this change of constness in terms of pointers and in terms of references. Right? So this is how the const operator, const cast operator can be used. Now, you could still do this in C style. This is how you will write it instead of const cast for print. I'm on slide 15. This is a C style cast, but naturally you will not be able to find it easily. You will not know that you have done this cast to remove constness. You could have done this cast to, make a int star pointer into cast star pointer also. So whole of that semantics is lost. You can also do this casting to the temporary reference by a C style casting. Possible. You lose that semantic information. But what is dangerous is you can actually cast A to non-constant object by C style cast, because it allows you to do anything, everything. There is no semantics of this cast. You just take it and change it and do this. So in that process, you have actually changed the basic behavior of the object, which is risky. Right? So this is the basic difference between the const cast. This is basic behavior of the const cast operator. So, for example, you can see some more. I have a const member function here, M1, of this class type. Right. If I try to do some, I is a data member. Right. So if I try to, int I is a data member here. So if I try to do this pointer assigned V, then I will certainly get an error because I've done it. This is a constant member function.
Sir, we are not able to hear you.
Am I audible? I had lost connection.
Yes, sir.
Yes, sir.
I hope that slide is visible now on slide 16. So I can remove the constness of this object here by casting this pointer, which was pointing to a const type object, now to a non-const type object. And then I can make this assignment. So again, this is very risky to do, but I can do this by using explicitly the const cast operator. So for example, here I is not declared as constant, but I can declare a constant reference to I. So if I change I directly, I will not be able to do it. But if I change it, I'm sorry, if I change I directly, I'll be able to do it. But if I change it through this const reference, I will not be able to do it. But I can take that constness away from the reference by removing it with int %. Then again, I'll be able to change it. So that's the way you can play around with the constness. So you have a const integer here. You can create a pointer to a non-constant integer by taking the constness of the object away. And once you have done that, you can actually assign to that dereferenced object. So you're actually changing J through a roundabout way. Again, so, but this kind of a thing are very risky, because what can happen when you take this constness away, it can actually temporarily create a different object, and the changes may happen in that different object. Okay. So this was about the basic const operators, cast operators. So we will continue on the other cast operators in the next class. If there is any question quickly, I can take. Otherwise, we'll continue on tomorrow. Any questions? Any questions, friends? Okay, so today we have done two important things. One, we have seen the basic implementation mechanism for virtual functions. And we have started understanding about the cast operators. And the first important cast operator, const, adding or removing constness in terms of pointers and references primarily, is what we have seen. So we'll continue tomorrow and discuss about the other cast operators. Have a nice day, and let us close.